Hello, I'm Ben, and today I'll be presenting a fractional step method for solving incompressible buoyancy-driven flows. The motivation is to create interesting simulations like this. So the basic problem we're going to use to validate the solver is that of air convecting in a cavity with isothermal walls. The right wall is at T cold and the left wall is at T hot, and the top and bottom are insulated. We're going to use some dimensional scaling in order to get a nice governing equation that we can work with as few parameters as possible. And since we want to work with the incompressible equations, we use the Buoyancy approximation so that we can neglect density variation in all terms except for the body force. And so that gives us the full set of equations. The important or the most important non-dimensional number here is actually the Rayleigh number because it determines how strong our convection is going to be. With the fractional step method, we can use different discretizations in time for the different convective, viscous, pressure, and buoyancy terms. For convective, we use an explicit linear multi-step method, and then for the viscous terms, we use Crank-Nicolson, and of course pressure is treated a little bit specially with the pressure correction step. And the buoyancy term is actually done with Crank-Nicolson because we solved the energy equation before the momentum ones. Since we have a Crank-Nicolson discretization for the viscous terms, we need to solve implicitly for the temperature at the next time step and also implicitly for U star and V star in the momentum equations. To do this in an efficient manner, we use approximate factorization to split the matrix on the left-hand side into two tridiagonal matrices. Then we can solve row by row and column by column. For the first row of nodes at the bottom of the cavity, we can apply boundary conditions on the left wall, set the temperature equal to 0, and then we have those tridiagonal elements in the middle, and finally at the right wall, the average of those boundary nodes is going to be 0. At this point, we're pretty familiar with the standard pressure correction, so I'll just summarize the entire algorithm here. First, we solve implicitly for the temperature at the next time step, then we solve for U star implicitly, and we use the divergence of U star to calculate the increment in pressure. Finally, we update the pressure and velocity and go to the next time step. In terms of some general trends in the solver stability, increasing the Rayleigh number will generally require a smaller time step. In terms of the grid spacing, for Rayleigh number is 1,000. Having the grid spacing also requires to have the factor k, so there's probably a scaling proportional to delta x squared here. For the higher Rayleigh numbers, this seems to diminish somewhat as you can actually increase the time step as you decrease the grid spacing. So here are some results for Rayleigh number at 10 to the third. We obtained solutions for 16 by 16 grids up to 64 by 64, just to show that some values we're interested in are converging to the reference values. At this Rayleigh number, the momentum carrying heat in the horizontal direction is not very large, so our contour plots are almost vertical. So when the Rayleigh number increases, we also increase the buoyancy force, so the momentum carrying heat across the cavity is increased. So that's why we have these contours creeping over to the right side. In terms of the grid convergence, it's still relatively okay, but it's definitely worse than at Rayleigh number 10 to the third. When Rayleigh numbers increase to 10 to the fifth, the momentum imparted to the flow by the buoyancy is enough to actually create two vortices in the middle of the domain. But also, we can see that a 64 by 64 grid is actually not sufficient to converge in terms of the Nusselt number, which is something we're actually very interested in. Here I just want to present the velocity profiles on the midplanes and show that they're matching well with the reference pictures, but also notice that the velocity gradient for high Rayleigh number is quite sharp, so we probably need more than a 64 by 64 grid in order to resolve it properly. Finally, since we're dealing with heat transfer, of course we're interested in the Nusselt number in the cavity. We can find the local Nusselt number by taking the gradient of temperature at the left wall, and then averaging this local Nusselt number across the entire domain, we can find the average Nusselt number. And they match pretty well with the reference values, except at the highest Reynolds number, probably due to the grid being a little bit too coarse.